asymptotes? Asymptotes. Vertical or horizontal line. Sometimes it can be another line, another shaped line in another life of your math. But right now they're vertical and horizontal lines that the graph never gets to. So for a hyperbola, for just a basic hyperbola, which are the kinds that you guys have been looking at, something like this. This is the shape of that graph, and this part of the curve and that part of the curve approach x equals 0, but they never get there. And they can't get to x equals 0. X may not be equal to 0. This is important for later on in the test, or earlier in the test, I guess, because you can't divide by 0. So you can't have 0 there. So there's no value. So an asymptote is right here. At the same time, it doesn't matter how big you make x, positive or negative, you make it 1 over forever and ever and ever and ever and ever, right? It just gets smaller and smaller and smaller. It never gets to 0. No matter how big this is, that value of y never gets to 0. So this line doesn't ever get there. So the vertical and horizontal asymptotes are this and this. Those are the two asymptotes. That comes up a lot. Let's see. Don't forget to put k in when you write these things up. There's always some constant for all these variation equations. I tried to make little marks where I saw errors that made it so that you may come up with a different value. The number of square tiles it takes to cover a kitchen floor varies inversely as the square of the length of the side of the tile. So if you hold constant of the size of a room and you use bigger and bigger tiles, you use less and less number of tiles. Joint is direct, and then combinations are direct and inverse. Quadrants, 1, 2, 3, 4. 1, 2, 3, 4. So when you have this equation here, put a k in front of that, and then you make k negative, then for positive x values, the answer to this is going to be negative. So for positive x's, you end up down here. And for negative x's, everything becomes positive, because if this is a negative and k is a negative. So when k is less than 0, you're out here and here. When k is more than 0, you're out here and here. That holds true for all functions. When you think about y equals kx, that's just a linear function, right? Looks like this. Unless k is negative, and as soon as k is negative, then it looks like this. Anything else? Anything you want to ask about these? Those are just things that I saw come up. Don't forget the graph. I don't know if that was an oversight or if you weren't sure. You don't know? That was then, this is now. For 16, there's two sides to the graph. Inverse square function. For 16, you ended up with, you should have something like this and like this. When you're graphing something like 16, you can make a table in your graphing calculator and just look for nice numbers. Or you can do it in your head. 2 and negative 9 for number 16 would have been good. 3 and negative 4. And then negative 2 and negative 9. And negative 3 and negative 4. That would have been 4 really nice points to use because they were easy to fit onto the grid. So, you want to ask anything at all? It still holds true. If you want to retake to get a better score, you can do so as long as you do it within a week. So it'd be nice if you would do it during this week. You can always retake, but you know, you got to sit down with either Joan or myself, make sure that you understand all of your errors, and then set up a time to be able to do it. And I don't know what this week is like. I'm trying to remember. I think this is the last week of October, right? So I probably don't have meetings. Usually we don't. It's the first couple of weeks. But either way, we don't have those meetings until 3 o'clock, so you have extra time after school if you want to do it. So where did we leave off on Friday? I know, I'm just asking you in case you don't know. Which lesson? Grade 2. What's it about?
Standard.
Standard form. Linear combinations. So you've got combinations of something and something else, and you have multiples of each, and they add up to a constant number. So I think we started out with what? Price of hot dogs and price hamburgers, $2.50 and $2. And then we look at how there's food on the floor yet. Is this from you already this morning? You eating almonds?
What?
No. Made it.
You didn't.
Yes, I
You
did.
bounced out.
No, it didn't.
Go look at over at the recycling bin.
Really? How did it must have hit that
Yeah,
rim.
it bounced.
Oh, it popped all the way over there? That's cheap. You're better off eating it. Okay. So we looked at combinations of hamburgers and hot dogs that added up to what, $30 or something? Yeah. And what was it? 12 of them? 12 dogs? No, 15 dogs. 15 hot dogs and 0
Yeah.
hamburgers was one combination. If you bought all hamburgers, then it ended up being 12 and no hot dogs. And then there were like several combinations in between. I forget if there's 3 or 4 of them that work out to add up to exactly $30. So this is an example of a discrete function where we're counting exact numbers. Now the next one here is a continuous function, or it's non-discrete. I should call it non-discrete, because soon you will learn what continuous means in a little bit different way. But the second example has to do with concentration of, I think, acid or something. No, yeah, it says acid. So you can water things down, make them less concentrated. Acid is no different. When we talk about the concentration of acids and bases, or any kinds of chemicals, but most typically acids and bases, what we're doing is we're talking about molarity, which is like the number of moles per liter. Do you know what a mole is yet? M-O-L-E?
We talked about it.
Do you know Avogadro's number? You don't know Avogadro's number yet? No? Okay. It's the number of atoms in a mole of a substance. And it has to do with the atomic mass of a substance. So, you know, you're looking at the atomic mass of, like if it's an acid, hydrochloric acid, you know, the atomic mass of HCl is different than sulfuric acid, which is H2SO4 and HNO3. It's all based upon the atoms that are in there and what their atomic mass is. So when you have things that have more mass per atom, you have fewer particles in a particular constant mass. So when you make solutions, you have to take into account the mass of the actual atoms. And you might have more molecules with the same type of concentration if you're working with a chemical that has a lighter atomic mass overall. So in chemistry, they don't count the mass of a substance when they look at chemical reactions. Like, they don't look at the mass of this entire bottle. What they do is they count atoms. Because you've done balancing of equations. Have you done that yet? A little bit? In 8th grade?
I think we.
Yeah, he touched on it, like with photosynthesis and respiration. C6H12O6, which is glucose, plus O2, oxygen, turns into CO2 and H2O. But it's not like one molecule, one molecule, one molecule. It's one sugar and 6 oxygens.
I think we did that.
Did you? Yeah, you've seen it. You're going to see more of it in chemistry, I hope. But when you're doing that, when you're balancing equations, you're counting atoms. So when we look at substances that have a particular molarity, we're looking at how many moles are in a particular volume. And that those moles are based upon the mass of the atoms and how many atoms are actually present. So what they ask us for in example number 2 is they ask for a chemist to mix some number of liters of 2.5 moles per liter, which would be a molarity of a particular acid. And they're asking to mix with another acid that has a different concentration. That other concentration is 7.25 moles per liter. And in the end, what they want is they want to have a mixture that simply has 10 moles of acid, because then those 10 moles can be used to mix with another substance to have a chemical reaction where every single atom is accounted for. And that's a lot of what the early chemistry is that you guys work with, is counting up and accounting for every single atom. So it's like statistics with chemicals. And this is an example of a standard form or linear combination. Because what you have is you have kind of like hamburgers and hot dogs that cost a certain amount. In this case here, we have a concentration, but we don't know how much. So just like you had a cost of hamburgers, we didn't know how many. In this case here, we have 2.5 molar and 7.5 molar acids. And we don't know how much of this. We don't know how much of this, but we know when we add them together, that it's got to equal 10 moles. So if this is 2.5 moles per liter and X liters, and 7.5 moles per liter and Y liters, and then the liters cancel out and then we're adding moles together. Sort of like when we had $2.50.
It's 7.25.
Oh, is it 7.25? I'll change it. But it's just like when we had $2.50 per one hamburger plus $2 per one hot dog. And then what we did is we multiplied by the number of hot dogs, but I guess we used we use dogs, and we use hamburgers. And then what would happen here, this is a number of hamburgers and this is a number of dogs. And then we ended up with $30, so the units would cancel out. So back to that, I gotta correct. 7 1/4. Yeah. So all we have to do is solve this as a linear combination. The hardest part of these problems is setting them up. So if you think of them as rate problems, a concentration is a rate. It's a rate of the molarity per liter, the amount of mass that's in a liter, the amount of atoms in this case that are in a liter. And then it adds up to the number of moles. So it's moles per liter times liters, adds up to moles. So with this here, because a liquid could be thought of as not just being even liters or even milliliters, it could be tenths or hundredths or thousandths of a liter. You know, you could have just individual drops. This is going to be a function that when you graph it, it's going to be a line. So just looking at a graph with this, if we have, what am I doing? Why did I do X there? If we have this 7.25 molarity solution graph here, and we have the 2.5 molarity graphed horizontally. The way to go about graphing this is to think to yourself, well, if I have 0 of x, how much y do I need? Because then if I have 0 of x, I can ignore this part of the equation. And I can just think of this as 7.25y times 10. And then over here, the y value is going to be whatever 10 divided by 7.25 is. Should I go faster than you? 10 divided by 7.25. What did you get?
1.3.
Michael, can I have your attention real quick? If you need to take a picture retake, please go to the elementary gym now. Picture retake right now in the elementary gym.
1.379
Yeah.
liters. And then if we're going to find the x-intercept, we would set y equal to 0. So this gives us the y-intercept up here, which is, I'm going to say that it's exactly that fraction. And then the y-intercept is going to be, if I set this equal to 0, 2.5 times 4 is equal to 10. So we come out here, and this is going to be 4 liters. So if you wanted to have a total of 10 moles, you either have to have a whole bunch of this concentration, 4 liters of it, or you have to have about 1.4 liters of this concentration, or any combination in between, anything at all. So if you look at what they want, they say to write an equation, we have that, and then how many liters of the 7.25 must be added to 1.5 liters of the 2.5 to get 10 moles. So if you're going to look at this on a graph, this is the 2.5, you come out here to 1.3 and you say, well, there, that's the amount that I need, which is an estimate. But if we need an exact amount, we're just going to say, well, 2.5 times 1.3 plus 7.25, and we would solve this equation here. That would give you an exact amount. So 2.5 times 1.3, how much? 3 1/4. So if I subtract that from both sides, this 0 cancels. 7.25y is equal to 6.75. Divide by 7.25. it comes out to be about 0.93 liters. And it says to answer to the nearest tenth of a liter, so then we would say 0.9 liters. But if you were working in a chemistry lab, you would not estimate. You would use another technique called titration, which allows you to measure drop by drop with a color indicator that changes color when you get the exact amount added in that you need. But you would have an idea of where to start from. So, your homework numbers, page 160. 1 to 7, 11, and 14 to 16. Oh, 14 through 16. I'm sure it's not a comma.